I want to do an explanation of the instantaneous rate of change formula that you see on the worksheet for section 3.3 and in the section for 3.3 in the book. So instantaneous rate of change is defined to be the limit as h approaches 0 of f of a plus h minus f of a divided by h. So what does this mean graphically speaking? Let me just try to explain this with a graph, what we're actually looking at here. So suppose I have a function. Let's say this function is, I don't know, something like this. And suppose that I want to find the instantaneous rate of change right at that x value that I'll call x equals a here. And this is some function f of x, and these are x values that we're looking at. So the idea is instantaneous rate of change can be interpreted to be the slope of the tangent line right here. The tangent line would be the line that just basically touches the function right at that one x value right there. To find the slope of a line, though, we generally need 2 points to do that. So the way that we have to get around the fact that we only have 1 point is we have to deal with limits. So what we do is we pick another point out here, which I'll call, well, actually I'll just define the horizontal distance between these two points to be h. That's where this h is coming from in the formula. So this x value then, if this distance is a and that distance is h, then this distance is a plus h. So that's that x value right there. And if I were to define these points, I would call this point, it has y value f of a. So this point, if I were to label it as something, I would label it a f of a. That's this point right there. And then this point right here, it has output value f of a plus h. That's the value that we get out of this function when I plug that x value into it. So that's going to give us as a point a plus h for the x coordinate, and then f of a plus h for the y coordinate. So that is what that point is, x and y coordinates. So what we first want to think about is the slope of the line that is going to connect these 2 points. Okay, so that's this line right here. This line is called a secant line, by the way. Let's go ahead and write that. It's a secant line. Its slope, the slope of this secant line, is just defined the way that we would define the slope of any line between 2 points. It's the change in the y values. So this is f of a plus h minus f of a. That's the change in the y values. So that's a y value, that's a y value, divided by the change in the x values. So that's a plus h minus a. But really, we already see that that's h. That's the change in the x values here. So the a's are going to cancel, and we're just going to be left with f of a plus h minus f of a divided by h. Okay, it turns out that the slope of this line is also known as the average rate of change. That's the formula that we had seen before. Although with things labeled a little bit differently, but that is what that is. It's the average rate of change. Okay, so what the idea here then is that, and I'm going to use different colors to finish this up. The idea is that we want to then imagine what happens if I make this h value smaller. So suppose I make the h value just this big instead, and I stop it right there. That would have the effect of bringing this point closer. And then what I would be doing is finding the slope of a new secant line. So I'd have this new secant line here. Now notice that that secant line has a slope that seems to be a little bit closer to the slope of the tangent line. Let's go ahead and draw the tangent line in there as well if I can. It's getting a little busy here, but the tangent line itself would be, again, the line that would just basically just glance that function right at that point, a f of a. So the idea is that as this h value gets smaller, if this is a new h value that we had here, suppose that this was some new h value that we did, this new secant line here would have a slope that's a little bit closer to the slope of the tangent line. So when we actually bring that h value really, really close, you find that the slope of the secant line and the slope of the tangent line are basically indistinguishable. And that's where the limit comes in. We shrink that h all the way down to virtually nothing. And then what we get out of that is the slope of the tangent line, which is, I guess, right here. So the slope of the tangent line would be what happens when you get the limit as that h value shrinks down to nothing. And then that actually gives you the slope of the tangent line. So really all we're doing is just putting a limit in front of this quantity here. So that's f of a plus h minus f of a divided by h. And so again, the secant line is an average rate of change between two particular x values. The tangent line is the instantaneous rate of change right at that a value right there. So, if these functions were maybe position functions, if this was a position function, what you might consider that to be is the average rate of change is like your average velocity over a particular time interval. The instantaneous rate of change would be how fast am I going at an instant in time. That would be like what you're looking at when you look at the speedometer on your car. So anyway, that's hopefully a bit of a help for you for figuring out what the instantaneous rate of change is versus the average rate of change.